Welcome, everybody. This is part two of our discussion about the latest Anthropic articles. So last week we went through a lot of the background, the mechanistic interpretability, conventional wisdom so far from earlier research. I'm going to recap that super quickly, but for time purposes, um, we really can't slow down or else we'll never finish the conversation. So I'll go through that real quickly, and then we're going to talk about the technique used. And so really it's probably going to be in the next session that we really get into the interesting findings. So for people who are interested in how to reproduce and some of the internals, this session will really dive into that. For people who really like, hey, I don't care how you came up with results, just tell me what you found out the LLM is doing. That'll likely be next week. All right. So, quick timeline here. 5 years ago, we've got the distill circuits thread, and that was looking at CNNs and stuff that today I think pretty much everybody considers conventional wisdom. The earlier layers will do simple things, edge detectors, horizontal lines, vertical lines. You combine those, you can get triangles, circles, textures. Eventually, you can have shapes like a face or a hand, and you can compose those and until you get to sort of the latest layers of the model, and then that's where things might be composed to say, hey, this is actually a person or something like that. So mathematical framework for transformer circuits looked at attention, and then after that, a lot of the focus has been on understanding the way information is represented in the model. And the next few slides, we'll briefly get into the idea of superposition when you have more ideas you want to represent than you have dimensions in your model space. So super briefly, if you know what a transformer is, we've got MLP layers, we've got attention layers, super oversimplified, but the MLP layers cannot see any other tokens. There's information that can be copied to the current token position, but the MLP can only operate on it after it has already been copied to this token position. So these are just information processors. They can look up facts, they can do certain kinds of calculations. The attention layers have special patterns that they learn when you train the model, and they will selectively match certain patterns. An example I give, which may or may not actually be realistic, is if you have a pronoun like she, then there may be an attention head in a relatively early layer that goes and looks for what is the noun that she is referring to. And it might copy information from an earlier token position so that if we know that the subject of this paragraph is Maria and Maria is a chef, then possibly information about chefs is getting copied to the local token position where the word she is. So that then later layers, they're not just dealing with a random she, they're actually dealing with a she that they have information they know about, such as, she is a chef. All right. I will try to monitor the chat, but let me know if there's a question and I don't respond to it right away. Okay. And then final piece of terminology, the attention, the transformer model, sorry, when it was first written in the Attention is All You Need paper, drew the residual connections as sort of these loopy things that went around the main modules, the attention and the feed forward. If we slightly redraw it, it's you know the connections are all the same, but if we draw the modules on the left-hand side and draw the residual connection in a straight fashion, then when you stack the layers, you sort of see this idea of this super highway where the data can just flow through. And so if all the layers, I don't know how this would ever happen, but if all the layers output zeros, then basically what would happen is the information after encoding the token would just pass through completely unmodified all the way to the end and would get output as the next token prediction. So a mental model for what these layers are doing is they are pushing, pulling, twisting, tugging, rotating on the information that's living on this residual stream superhighway. It's possible for them to add to it. If they have a negative value, it's actually possible for them to subtract or erase things from this residual stream. And so the width of this residual stream, that's what we refer to as the model dimension. And when we think of that as being a vector space in which our information lives, then when we talk about the dimensionality of that vector space, what we're really talking about is that model dimension. So super briefly, the linear representation hypothesis says that directions, that the residual stream is a vector space, and that directions in this vector space represent concepts. If we have a 4,000 dimensional residual stream using linear algebra, you can represent 4,000 concepts in orthogonal directions and have perfect recoverability where if you do the dot product with a canonical vector, then anything that's in the direction of that vector will match, and anything else, because all the other directions are orthogonal to it, will give you a 0 on your dot product and will not in any way interfere with the calculation of what you're trying to measure. So if you only had 4,000 concepts, you can represent them perfectly using an orthogonal basis. However, in LLMs, we expect that they have hundreds of millions, if not billions, of different concepts they're trying to represent. And even the largest of LLMs, we're still, on the order of tens of thousands, of dimensionality for our residual stream. So what happens when you have more things you want to represent than you have actual dimensions to represent them? And we're going to get this phenomenon where either if information is not sparse, it's just going to pick the top. So if you had concepts that constantly appeared together over and over again, then the LLM is going to get the lowest loss, the lowest cross entropy loss for next token prediction if it represents the 4,000 most frequently occurring concepts in your language. But if you have sparsity, then it can do things like in this case, it can represent 4 different concepts in the plane, and any pair that are opposite each other, if they're both present at the same time, will interfere with each other, but they're otherwise completely independent of all other concepts. And if you have even higher sparsity, then you can represent more than 4 things. You can even represent 5, 6, or 7 things. And now you run the risk that all of them will interfere with all of the other ones. So you cannot, in this diagram here, if you have these 5 concepts, you couldn't have, say, 5 baseball things represented here. Pitcher, catcher, strikes, home plate, baseball diamond. You can't have all of those because they're going to occur in the same passage, in the same sentence or paragraph quite often. But if you had things like the Eiffel Tower and a baseball concept and some detailed biology concept and some very obscure archaeological term, right? These things, if they never occur in the same sentence, if what you're doing is taking dot products, it doesn't matter the fact that these other 4 things would have non-zero dot products because they're never going to show up at the same time. All right, that's a very, very brief explanation. And so what ends up happening then is we know from sparse coding that we can actually, with high probability, recover all of these different concepts as long as the sparsity is very high. The co-occurrence rate is extremely low. The other thing that then happens that's a little bit hard to explain is that individual concepts are represented as linear combinations of the actual components that you have. So if you know anything about like sparse coding and how that's read out, you can't read it out individually because that's basically how you read out monosemantic things. What you have is you have constructive and destructive interference between these patterns that you get from multiple nodes. And again, if you know the coding pattern, then what'll happen is seemingly to me a little bit like magic when you have this one concept of the Eiffel Tower, and then you combine these different elements, they all have like non-zero values, But amazingly enough, if you have a pure Eiffel Tower concept, then what happens is in your first floating point, you have a point two, and then you have a negative point one, and a point three, and a negative 0.15, and blah, blah, blah. And when you sum them all up, magically you get a zero. Okay. And so that basically things, become readable as pure individual concepts. All right. Again, I'm going very fast for the through this because we went through this last week. So then the other thing to just mention briefly is that the attention layers were really talked about in the mathematical framework for transformer circuits article, the very first one in the transformer series. And what they talked about is that essentially each attention head is reading from the residual stream, and realistically, it's reading a subset and not the full width of it. So you can think of it as reading from a subspace. It's drawn here contiguously, just uh, for ease of visualization. But it's not like if you have a 4,000 dimensional residual stream that it has to read, um, if you have four attention heads, it doesn't have to read 1,000 consecutive floats from it. It really can read any up to 1,000 dimensional subspace from it. And the main job is, as I mentioned briefly earlier, is to copy information from an earlier token position to a later token position. The other thing that's important about this is they clarified the concept that the queries and the keys calculate the attention pattern of which earlier token gets attended to and information copied to the current token position, but they do not directly contribute at all to the value that gets written to the current token position. They can only do their job of forming the attention pattern, which can be at most one for any token position. It could be spread out. It could be a quarter, quarter, quarter on four different tokens, but they have to sum to one, and the Q and the K will combine to determine that pattern. But it's really only the O and the V matrices that determine the actual values that get copied. So in today's paper, what we're going to see is that this is a technique to understand what the MLPs are doing. And so for that reason, on any given prompt, on any given text input, we're going to freeze the attention pattern. Okay, we're not going to study how the attention pattern formed. We're just simply going to say, I know that when I input this string, fact, the capital of the state that contains Dallas is that in all these positions and all these layers, this is what the pattern was. It was 0.75 here, 0.24 there, 0.001 there, 0 there. And so then they just copy those numbers frozen as is. That's what we're going to see in a minute. All right, so that was my whirlwind recap from last week. Attention moves information to the current token position. Concepts are represented as directions. Superposition polysemanticity means that you are going to read things out with combinations of neurons, and from compressed sensing, we know that we can recover these concepts. So then there was prior work on an architecture called the sparse autoencoder. And basically, if you're familiar with autoencoders, a vanilla thing is you might have an input that's 4,000 dimensions, and maybe you create a bottleneck. You create something that's only 250 dimensions in the middle. And so what that's going to do is it's going to squeeze to try and find sort of the core information that you have in your data. The sparse autoencoder does the exact opposite. It goes from 4,000 to, let's say, 4 million. Okay. And it's actually going up much, much higher in dimensionality. Well, if you think about it, a very simple thing that an autoencoder could do that would generate zero loss is it can just copy 4,000 of the inputs, and then it can have the other 3,900,000 all be zeros. And it will be able to perfectly reproduce the inputs. So you have to, in some way, induce it to do something different. And what we do is we have some sort of penalty that we apply to the middle of it. And so In practice, often what this has been is this is an L1 loss. Okay. And this is how you induce sparsity. It's very similar to if you do lasso regression for linear regression. So you apply an L1 loss, and what that means is anything that goes to zero has no more loss. So if your original input was 4,000 things, and they were all just a combination of, let's use a small number, of 10,000 different concepts. Um, but I think of this like when I was, maybe in elementary school, you might have, or maybe like first year algebra, you might have a problem like, hey, a farmer has chickens and sheep, and the chickens all have one head and two legs, and the sheep all have one head and four legs. If in total the farmer has this many X many heads and Y many legs, how many chicken and sheep do they have? Okay, you have two numbers that are not chicken and sheep, but from that you can recover because you know the pattern of one head, two legs, one leg, head, four legs. Because you know that pattern, you can recover the exact number of chicken and sheep. So in a similar way, we can do this with these concepts. And if you're able to extract the individual concepts, then they're going to have the smallest L1 penalty because they will have a single intermediate neuron, intermediate position that is non-zero, and then everything else is going to be zero when that concept is present. So you pass one sentence through, and the concept that's present is the Eiffel Tower. Ideally, your sparse autoencoder is going to have one non-zero value and 3,999,000 zeros, and then that L1 penalties can be tiny. And then in a different sentence, it's talking about cars, and it's talking about the Ford Mustang. And if you have a Ford Mustang concept in your autoencoder, then that will be non-zero and everything else will be zero. So that's the reason why the L1 penalty works, is because if you can separate all of the hidden concepts out individually, it'll have the smallest L1 penalty.
Hey, Ted.
So yeah,
I had a question about this. Julius and I were talking offline last week about this, but L1, so L1 is like the sum of the absolute value of all the activations. Is that right?
yes.
Okay. Um, so I'm not quite sure how that induces sparsity. So if I have a zero point 0.5 and a zero point 0.5, that's the same value as a 1. Like one value of 1 and two values of zero point 0.5 is the same under L1.
Yes, yes. So what you actually want is you want the L0 loss, the
Oh, okay.
L0 penalty.
I don't know
Okay.
what L0 is, but that sounds okay.
L0 is one if you have a non-zero value and zero if you have a zero value. So you
Okay.
get a penalty of one for any non-zero value. However, the L0 penalty is not differentiable. So you can't really use gradient descent on the
Okay.
L0. Okay. Right? It's like the delta function, right?
Okay.
So people use the L1 as a proxy for the L0 penalty because it's the next best thing. And in practice, usually what happens is um, you you do get a lower penalty if you can extract the individual concepts so that you have a one and a bunch of zeros. But you're absolutely right. You could have 2.5s, and that would fool the L1 penalty in thinking that's just as good.
Okay. I yeah, I'm just okay. You say it just works that way. I don't quite understand what would induce it to become more sparse.
Are
But
you familiar with how lasso regression works?
no.
Okay. Hold on a second. Let me see if I can find.
I don't want to derail you if you want to if,
It's
if nobody else is interested.
um, let's see here. Oh, it lost my. Uh, okay, here we go. This may not be the perfect image, but All right. Um, uh, when you do the L1, the Euclidean, sorry, when you do the L2 penalty, so you're using Euclidean distance.
Yep.
Okay. If you ask what is the contour line for Euclidean penalty? Okay, so where is the penalty all one? It's on the perimeter of this blue circle.
Okay.
Okay, and the gradients are going to be all perpendicular to this circle. So they're all going to point at exactly the origin.
Okay.
Okay. When you do the L1 penalty, can you see that in R2 that the
Yep.
diamond represents all equal
Yep.
uh, penalties?
Yep.
Okay, so these would all be ones. And if you look at the gradient here, it's again perpendicular to the perimeter. So they're all at various 45-degree angles, northeast, southwest, right?
Yeah.
Southeast, northwest, whatever order I said them in. All right. But they no longer all point at the origin,
Okay.
right? So if you started out here, okay, oh, sorry, the gradient is always perpendicular. It's at a 45-degree angle unless you're on one of the axes.
Okay.
Once you're on an axis, then the gradient points directly towards the origin.
Gotcha.
Okay. So
Okay.
if you started
Got it.
out at exactly halfway on here, you're just going to keep going until you hit the origin. But if you started out anywhere else, what'll happen is eventually you're going to hit an axis and then you will follow that axis. So what happens with this L1 penalty, if I find it much easier to understand in terms of like a linear regression, is that if you then minimized, if you started here and beta 1 and beta 2 both are shrinking by the same amount constantly, right? So um, on here, if you started out over here, okay, since you're moving towards the origin, maybe beta 2 is shrinking by a third as much as beta 1 is shrinking, and neither of them gets to zero until you hit the origin. Okay. But because this is a 45-degree line, it means that beta 1 and beta 2 are both shrinking at exactly the same amount. When one of them goes down by zero point 0.1, the other one goes down by zero point 0.1. When one of them goes down by zero point 0.2, the other one goes down by zero point 0.2. Whichever one was smaller, eventually it's going to hit zero. But once you hit zero, the gradient now changes. And now it is pointing directly at the origin. And so once beta 2 gets zeroed out, it will never go back to a non-zero value. It'll get stuck there. Okay. So the axes are like attractors in an L1 loss.
Yeah.
So that once you've landed on an axis, it'll never leave that axis. Okay. So if you ran gradient descent on some problem with this penalty, the parameters will move in a 45-degree angle, so to speak, no matter how many dimensions it is. It'll just keep moving on a 45-degree angle until one of them gets zeroed out, and then that one will stay zero, and all the other ones will continue to move a 45-degree angle, and then that will go until the next one gets zeroed, 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 zero, until you have only in the extreme, if you had an L1 penalty of 100 billion, then you could get to the point where you have only a single non-zero coefficient.
Perfect.
That and
There-
that
there-
and that's the sparsity because it's zeroing out the other elements and it's
Yep.
it's 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 choosing just right. So the idea is that you can't have an L1 penalty that's too large, or you only get one non-zero element and everything else will get wiped out because all you're measuring is the penalty. You're not measuring the original signal. But if you get the coefficient on it just right, then you get this balance where it'll zero as many things as it can while still maximizing its representability, which is retaining all the original concepts.
Perfect. Very nice. Thank you very much.
All right. So we'll see a little bit more, although I wasn't planning on spending the time in today's paper, but they do cover this. Well, they show you the equation. They don't explain why it works, but they show you the equation. Uh, so this sparse autoencoder found that we could take the residual stream that's 4,000 and blow it up to say 40 million, and maybe a half of those would have human interpretable clear patterns where it's like, let's pass this corpus through. let's pass through 100 million different sentences and like, oh, look, this particular activation number 17 million, right? 234,000, 197, it lit up on 20 sentences. Let's take a look at what those 20 sentences seem to have in common. And then you're like, huh, wow, that's pretty crazy because the first sentence is the Golden Gate Bridge is one of the most popular, landmarks in San Francisco. And then the next sentence is the Golden Gate Bridge was architected by blah, blah, blah. And you look and at every single one of these sentences mentions the Golden Gate Bridge. Okay. So you're like, I'm pretty sure that this feature is the Golden Gate Bridge feature. And then they did some experiments. They did some ablations in earlier work where they could take a sentence that had absolutely nothing to do with um, the Golden Gate Bridge. Okay. Like, what is your favorite sandwich? Okay. Um, and if they just took that particular direction that they found using their sparse autoencoder and they artificially added it onto the residual stream um, in certain places, you know, then what would happen is the sentence completion you would get would be something along the lines of, my favorite sandwich is peanut butter and jelly. I like to eat them on the Golden Gate Bridge. It'll just add the Golden Gate Bridge to any sentence, even if it has nothing to do with architecture or San Francisco or anything. Okay. And so that kind of experiment seemed to confirm that this direction really is. It's not just a coincidence that those 20 sentences that mention the Golden Gate Bridge, right? We're able to do positive and negative ones. So that's a positive experiment. We could do a negative ablation where you you talk about something like like whatever, I don't know, bridges, landmarks, whatever in San Francisco, and then you subtract from the residual stream the Golden Gate Bridge direction. And it'll be like, oh, the Transamerica period and the Bay Bridge and Alcatraz, and it will never mention the Golden Gate Bridge because you've subtracted it out. So they've done both positive and negative ablations to sort of show that. So we have this idea that we have these concepts, but up till now, we didn't know where the concepts came from. We were able to show that they're there, right? So we're able to see that there is this Golden Gate Bridge concept, but we don't know why the LLM, how the LLM got that concept onto the residual stream. So in the work we're going to look at, and today we're really more going to be focusing on the building blocks, the technique. We're going to study just the MLPs, not the attention layers. And in selected sentences, not all sentences, this is not boiling the ocean, this is not solving everything. In selected sentences, we'll actually be able to see very distinct patterns where this MLP or this set of MLPs in earlier layers seem to correspond with the Golden Gate Bridge, seem to correspond to, um, you know, stakes, seem to correspond to the color green, whatever. Um, and when they appear in certain patterns, then that promotes other concepts later in the LLM. And then those things promote other concepts. And then ultimately, in some sentences, we'll be able to see very distinctly that, say, 75% of the causation for a high logit for Austin being the next token comes from this particular tree of concepts. And that's what the on the biology work is going to show is specific trees that they were able to find that this circuit um, is what predicted the next token. Make sense?
Yeah. When you were talking about this experiment injecting
Mhm.
through these autoencoder probes, I guess, like a Golden Gate Bridge, was that at a single level or did they do it kind of simultaneously at multiple levels?
There's been so many papers and I haven't read them all, but the ones that I'm most remember reading, they would inject it in one place for
Okay,
simplicity.
interesting. Okay.
Yeah.
Is this the first paper that's related to MLPs to particular concepts?
Uh, yes. Well, the first main article, there's like monthly updates and things like that, but this is the first main article. Uh, um, although the MLP itself is deceptively simple in architecture, what it's doing up till now has been very difficult to describe. See, attention, as much as it's far more complicated than an MLP, when it takes when you see an attention pattern that's really strong, like something very close to one and a whole bunch of zeros, it's very clear which token position it's looking at. And then you can see what numbers is it writing to the residual stream. So you can kind of say, like, independent of everything else, I know exactly what this thing is doing. Um, for an MLP, if it just dumps a bunch of numbers onto the residual stream, it's a little bit harder for you to understand what did it really do? Because right, so in that weird sense, even though attention's more complex, it's a little bit more telltale when it does something, kind of what's going on. You have this hint that's like, oh, it was really looking at token 10 and it was writing it into this position. What do I know about these token positions? And you're like, well, this current position is she, and position 10 is where it has the name Maria. I think I know what it's doing. You know what I mean? That makes sense. Some sense as a partial explanation.
Doesn't it have the same problem though with attention that you don't know if there's like a superpositioning going on? You may be
Yes.
injecting multiple things simultaneously. It's not necessarily one concept.
Yes, and so that's why we ended up needing a couple years and some very some failures and some what we'll see is complex design in order to be able to pick out that superposition really well. And even
Oh,
then, it works yay much. And they had I'm assuming they had to work to find particular sentences where it was very clear what's going on. But if you just picked a random sentence, it might not be at all obvious, even
mm,
with this technique, what's going on.
mm.
Okay. All right. So moving over to the article. Uh, so this is the companion article called Circuit Tracing, Revealing Computational Graphs in Language Models. And ultimately, we're going to explain what these two um, uh, pictures mean. Okay. Um, so again, the goal here is to model what the MLPs are doing um, as accurately as possible. We are not going to be explaining attention in this. So they give across a little roadmap here. I'm not going to go into detail because that's really what the whole rest of the article is, but uh, they're going to talk about transcoders, and they're going to talk about cross-layer transcoders. From this, they're going to build graphs of connectivity from different MLPs in different layers and different token positions that they call attribution graphs. We're going to have linear attribution between the features in these graphs, and that's really important because when things are linear, it is very easy for us to quickly, efficiently calculate exactly how much influence everything has. Okay. Um, then we're going to do pruning wherever there's very small values because again, if you have an LLM, you're going to have millions of concepts in every layer, and that's just way too many edges to keep track of. So we have to get rid of all the small ones um, and um, keep only the big ones. And even then, it's still pretty ugly and complicated. So then they group certain nodes together to say that they're doing similar things. These all seem to be related to the Golden Gate Bridge. Some of them might be a little bit more focused towards San Francisco-ness than Golden Gate Bridge-ness. Some of them might be a little bit about tourist attractions. Some of them might be a little bit more oriented towards architectural objects. But they all do seem to be kind of Golden Gate Bridge focused. And so they're not identical even remotely, but we're going to lump them together because otherwise, again, the graphs, even at 40, 50 nodes are a little hard to interpret. But if we can boil it down to a graph with 7 nodes, then it's a little bit easier to, um, you know, uh, talk about it and see what's going on. They built an interface for being able to look at the graphs. And then ultimately on the biology paper, which is where we're trying to go to, they're going to do validation experiments. And the important thing is, we have to get rid of all the small ones. So we have to get rid of all the small ones and even then, it's still pretty ugly and complicated. So then they group certain nodes together to say that they're doing similar things. These all seem to be related to the Golden Gate Bridge. The validation experiments are going to be done on the real LLM, not on their interpretation of it. Uh, so, um, so that's like where I was saying, like you inject the idea of Golden Gate Bridge or something like that. They're going to do very specific experiments based on the graphs. Um, and so then uh, I think that the validation experiments, these ablations, are very important as to why I feel that this work um, has makes accurate conclusions about what these computation graphs are, what these circuits are. Because if the circuit was something other than what they did, then when you do a very tiny experiment in a small number of locations, it won't necessarily have the effect that you want. But if the circuit is correct, then if you snip in just the right place, you can zero out and eliminate a certain behavior. Or if you add in just the right place, you can cause certain anomalous behavior. They also have this conversation about global weights that honestly I didn't follow as well, but if we want to, we can take a look at that at the end of the article. All right, so that's our roadmap. And so let's dig in. So the first thing we're going to talk about here is this cross-layer transcoder. And the idea of this is that we are going to build something that predicts what the output of every MLP is, given we know what the inputs of that MLP are. Okay? This is a little bit sophisticated, and this is like 2 years worth of research sort of led to this particular architecture. So I think if we just take a moment and look at one of the earlier articles, um, they they give a little bit of information. Okay, so the basic idea here is in our sparse autoencoders, um, we had the idea of this very dense information that's running on the residual stream, and we could break that out into its component individual monosemantic concepts. Okay. If we built the perfect sparse autoencoder, it would exactly break things out. But there is this problem once you start talking about layers that this here is the way we kind of draw multiple layers with these plus signs as residual connections. Okay. But conceptually, this gray diagram on the left is equivalent to this gray diagram on the right. Okay. Um, and so, uh, um, well, maybe it's not identical, but anyway, the point is you can think of these two components as having a largely working in parallel. Okay. Now, it is entirely possible for them to work serially, where there's this dotted line connection here that goes from the output of the first one to the input of the second one. But let's just say they happen to work independently, and there was nothing that the second one was using the first one. Then you can think of them as running in parallel. So what makes life even more complicated is that if you have this idea of being able to split out a very dense residual stream into sparse concepts, you actually could have it split where the left half is in one layer and the right half is in another layer. So early on, what people did was they tried building, yeah, so the idea is then you can stack these side by side, and this is the true behavior for reading out this compressed sensing. So where's the picture? Early on, um, people tried creating these transcoders where basically I would take a single MLP and I would predict the output of that layer 17 MLP. Okay. But it didn't work as well because of this problem up here, where maybe the layer 17 MLP only had half of the story and the layer 18 MLP had the other half of the story. So for that reason, they said, what we really need to do is to build a cross-layer transcoder, which in this diagram, they basically say, we read in parallel all the inputs to all the MLPs, and we predict the outputs from all the MLPs in parallel all at once. Okay. Now, there are some rules. So just like you have like autoregressive masking, um, um, uh, if you look at sort of the orangey brown wires on here, what you'll see is that this particular input to layer 2 cannot affect the outputs from the layer 1 MLP, okay? But things do flow upwards, okay? And so if you said to yourself, like, without these diagonal lines, with just the horizontal lines, we'd be predicting each layer one at a time, okay? With these diagonal lines, it's more complicated, but again, this diagonal line right here that goes from layer 1 to layer 2, this is what allows us to say layer 1 got half of the story, layer 2 got the other half of the story, and between the two of them combined, we have this one concept from linear combinations. Okay, so it's no longer linear combinations within one MLP. We now allow linear combinations from multiple layers MLPs in the way we build this transcoder. And so this CLT is obviously more expensive to train than it would be just to do it one layer at a time. Okay.
So this is going to be for all the layers in the language model.
Yes. So if you have a 36 layer model, instead of training 36 one layer transcoders, now we
Yeah.
only have to train once. Yay! Good news. But it's a 36 times more complicated thing that we're training, so to
Right.
speak. Okay. And they have some details in here where they show some data that proves that the amount of error that they have from this CLT is lower than the error you get from 36 individual layer transcoders. It's doing a better job of picking out these concepts. Okay. So we're not going to go into too many more details, but I will show that um, if you look here, the sparsity penalty, this L sparsity, okay, has our magic constant lambda here, okay, um, and the the really weird thing that they do that I think is kind of clever um, is here you can see there's the weights, and they're taking the norm of this, and do they actually say that this is the L1 norm or not? Or I'm not really sure. But the cool thing that I've not seen until this paper is that they then run a tan H around this. Okay, so they scale it with a constant C and they run a tan H. And so tan H basically is bounded between -1 and 1. And for very large values, you're going to get a 1 or a -1. And for small values, you're going to get a 0. And so this tan H is actually imitating L0 loss, but it's fully differentiable. So I think this is kind of a clever trick. So this tan H probably works better than L1 loss. Well, that's why they do. That's why they used it, right? I'm sure they started with L1 loss, but then somebody figured out that now it's not true. There's going to be a region in which tan H is going to give you values between 0 and 1. Okay, but I think the idea is they wanted the tan H to very often give you 0 and very often give you 1 or -1. Okay. Um, and again, the idea is that this then gives you a differentiable imitation L0 penalty.
I would assume that C can be adjusted during the tuning process as well, right?
Yeah. So let's see here. No, it looks like they say it's a hyperparameter. So it may have been fixed before training and just they ran multiple trainings with different values of lambda and C.
Mm.
Okay. But the idea is to try to get tan H to act like L0 loss.
Yeah.
And then, of course, the lambda is the strength of the penalty because too big, you start losing data. You start losing a lot more data. At any penalty, you're losing some data, but you start losing a lot more. And then too small, and it's not enough to encourage sparsity. Okay, so now that we have this single cross-layer transcoder that we've trained for the entire model, what we can do is this diagram I found a little bit hard to read, but if you can imagine that each of these squares is an MLP, And what we've now, for some reason, just completely not drawn the attention or any of the other components of this model. We've just simply drawn the MLPs. The MLPs are a certain size, maybe like 16,000 or something like that. And our CLT might be something more like 40 million. Okay, so this is really not quite to scale, but the idea is that we will have many, many, many different circles here that are the monosemantic activations in the middle of that autoencoder. Okay. Actually, I don't think sorry, I went a little too fast. I didn't show this CLT. Um, it's there's not a diagram, but if you see here, there's a weight for the encoder and there's a weight for the decoder. So it's a two-layer thing. It's just like a simple autoencoder. Okay. So when we talked about autoencoders where you just have two layers. The first one, in the case of a traditional autoencoder, shrinks it to a smaller bottleneck number of dimensions, and the second one reconstructs. In this case, we blow up to a higher number of dimensions, and then we shrink it back down. Um, and either way, we're reconstructing the original. And so they have a reconstruction loss here, which is just L2 loss, and then they have a sparsity inducing loss. And so when you combine those two, then basically that's how you hope to get monosemantic concepts in the activations in between the two layers. So each
Hey,
of
Ted,
these
what
circles
what's
represents
the jump? What's the jump, Raylu? Do you know what that one
um
is?
it's not important.
Okay.
I had to look it up, but basically ReLU is 0 for everything that's negative,
Yep.
and it equals the input.
Yep.
Um, and jump ReLU, I believe, is just it's 0 for everything negative, the same. But for positive things, it equals the input plus a bias. So it jumps that 45-degree line
Oh,
up
okay.
away from
Gotcha. Okay.
the 0 line to the left.
Okay. A discontinuity.
Yes, I don't know why that's better, but it
Okay.
does obviously intuitively it more strongly separates your positive and negative values. Because
Yeah.
even for a very tiny positive value, it's now very different,
Yeah. Gotcha.
right? Um, Okay, so it's not really quite to scale. The idea is that a 4,000 um, dimension LLM might have a 14 or a 16,000 hidden dimension in the MLPs, but this sucker's going to be way, way bigger. This sucker's going to, like, again, be like, say, 40 million or whatever. So the circles doesn't quite do it justice. And the hope is that every single one of these circles, which represents the activations in the middle of the autoencoder portion, or said another way, it's like a column from the output of the encoder layer. Okay, so hopefully every single one of these 40 million things is now a monosemantic concept. It's the Golden Gate Bridge and the color green and everything that the LLM itself has as a concept. So we're not going to get into all the details, but there's the desire that we can prove that these are not just directions we can extract, but actually truly the directions the model is using for internal computation. Because you can imagine, right? We could somehow maybe build a fancy architecture that just gives us concepts that we want to see, not the concepts that the model was actually using internally to do calculations. So that's why you have to do some of these ablations to show that this really is something that is important to the functioning of the LM. So if I just came up with this thing that says, hey, the eyelashes on a human are super, super important to vision. They are the mechanism by which people are able to see. And then you trimmed somebody's eyelashes off and they could still see perfectly fine, then that says that my hypothesis is pretty much bunk, right? But if you say it's the optic nerve and you trim that and only that, then you make that small change and people can't see anymore, then that says, oh, well, that strongly supports your hypothesis that this one little thing is critical to vision. Okay, so The idea now is we've taken all of the MLPs away and we've replaced them with the outputs from our cross-layer transcoder. We're going to say CLT from now on just because cross-layer transcoder is kind of a mouthful. So we build a replacement model where we've replaced the MLPs with our CLT, but otherwise left everything else in place, the attention layers and everything else that the model does. And I'm imagining some researcher said, let's now see if we can interpret everything that's going on in this model, in this LLM, using this replacement model. And sadly, it was still way too complicated and they couldn't figure out what the heck was going on. So they then took it a step further. Okay, so here's some of their stuff where they're like, hey, our CLTs work better than the per layer transcoders and some stuff like that. So they then went to another step and they said, okay, that was still too complicated. So what we're going to do is instead of having a generic architecture that runs on all prompts, we're going to analyze the behavior for each and every text prompt individually. So they call this the local replacement model, meaning it's local to a given prompt. So if you have the prompt, like I was saying before, this is from their first example, fact, the capital of the state containing Dallas is, okay, we're going to analyze just what's happening for that and only that sentence. And when we do that, what we're able to do is we're able to say, hey, what's going on with attention in this sentence? Oh, well, in layer 1 at token position 3, the attention pattern is 0.7, 2, 0.01, 0.15, blah, 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 blah. And at every layer and every token position, we can read out what that attention pattern is. And then we don't need to calculate that anymore. We can just freeze those as fixed constants. The layer normalization modifies the data, whether using whatever kind you're using, layer norm, RMSE, they're modifying the data. Instead of using that calculation, we just freeze the net effects of what it multiplies by what it adds as a bias. So if you do all of that, then all you have are these frozen constants and your CLT. There's nothing left of the model because you've frozen everything else out. And what that means is then, having gone from a real replacement model, we have this local replacement model. We don't need anything other than these CLT monosemantic concepts because everything else is just a constant. They're not. It's not actually doing anything anymore. They're just for example, attention is just the wires that are in between our monosemantic concepts, okay, with constant values on them. That didn't quite work. So then the final thing they did to make this local replacement model more accurate is they measured in the real model what was the output of the MLP at layer 5, and what did the CLT predict the output was. And then they found what the difference was, the error in that output. And then, so if all of our monosemantic concepts are circles, everywhere you see a diamond, that's actually the actual error of the CLT's prediction at that layer for that token position. And what this allowed them to do is, one, to faithfully propagate signals from layer to layer, because now instead of just using your approximate layer 1 output and then going into layer 2 and then compounding the errors and having your layer 2 output and then compounding that error and so on, right? So you go through 24, 36 layers, these errors can really compound in a very nasty way, where now your replacement model is very, very far away from what the actual LLM did. In this case, they still have errors, but they're catching them at every layer. And so they don't compound anymore. Ultimately, then, what they do is they see we've got all of these circles, these monosemantic concepts, connected by various weights via the residual stream, via the attention patterns and whatnot. And because all of that is linear, then this becomes a very, very straightforward linear graph, and you can do very, very simple math to figure out, like, like how things from down here sum together in later layers and things like that. And so ultimately, you can calculate a net strength of like if this one were 0 versus if this one were 1, how much would that change this concept up here? Okay, and so you can compute the pairwise strength between any node and any other node. And then they prune away all of the values that are close to 0 to try to get a graph that looks like this on the right. So this attribution graph is after they've pruned everything away. So what can happen is you can have like this diamond here. This is an error node that goes towards predicting the next token. If a whole lot of the weight of that final prediction came from error nodes, then that means that your replacement model sucked and it didn't do a good job of predicting what actually happened. The error was required to fix all of the predictions. However, if you say in this particular sentence, only 5% of the next token prediction can be attributed, because remember, we have pairwise weights between the next token and every single node, including the error nodes. And so if you sum all the error nodes and they only contribute 5%, then you could sort of argue that our graph has captured 95% of the calculation. And we can have a fair amount of faith that this attribution graph is accurately capturing the internals of this LLM. All right, I've been going a long time, so I should probably pause to see if people are following, if people have any questions before we go on. We're pretty far, so we've covered a lot of ground. Okay, great. So then there's two steps of throwing things away. So one thing we throw away is any of these connections between nodes that are very close to 0. The other thing that can happen is we can have a really strong connection between, say, this node here and this node above it. But this node above it makes no contribution whatsoever to the next token prediction. Okay? So let's just say we have the word capital and it's strongly associated with dome, a building with a dome on it or something like that, right? So there's a very clear connection that capital promotes the concept dome, but dome has absolutely nothing to do with the next token prediction in this sentence. That's why you see this little trash can above this node here. So these are nodes that were promoted intermediately, but then ultimately these nodes had no causal effect on the output. So these are real things that happened. And so you can imagine you can have the word Texas, and maybe somewhere here it's got Rio Grande, Mexico, the Alamo, many, many concepts that are promoted by Texas, but those concepts in this particular sentence had nothing to do with the next token prediction. So that's where these trash cans lie. These are things that were strongly seen in the interior of the model, but did not influence the next token either up or down. They just died. And so if you imagine the idea that if you mention the Eiffel Tower in a sentence, it's possible that the height of the Eiffel Tower, the architect's name, I don't know who it is, Paris, France, the fact that it's made from metal, I don't know, steel, its height, all of these, the year it was built, right? The whatever World's Fair or whatever, all of these facts might actually appear in the interior of the model. But if you ask it, if the sentence is fact, the Eiffel Tower is located in, then maybe most of those things, like who the architect is, are just dead ends and don't actually end up contributing to the next token prediction, Paris. Okay. So there's two kinds of pruning, right? There's edges that have no importance, and that means that these concepts aren't connected. And then the second kind of pruning is there are concepts that are connected, but in this particular sentence, they don't lead us anywhere for next token prediction. So in a different sentence, this would be an important pathway, but in this particular sentence, it's not. So the dotted lines here represent concepts that are strong and visible, but but don't matter in this particular sentence.
That question there, actually.
Yeah, your audio's really low.
Oh, is it? Okay, one second. Is that any better, perchance?
Yes, thank you.
Okay. Um, does this work in the opposite direction too, do we think? That if there was some way to engineer that the capital example is what made me think about it. So like for the sentence, like the capital of blank is blank, and things like dome or steel or whatever random other stuff pops up but technically doesn't contribute to the next token prediction. Um, if you change those, does it
Fine.
well, actually, no, I guess thinking it through, then if you change those, then since they don't have an effect on the next token prediction, then you would still end up with that exact same sentence, regardless of if those random things were other random things. Do I have that correct?
I mean, so there's some kind of experiment we could design where we change it at the end, where like instead of the capital of, right,
Mm-hmm.
say, okay,
I'm wondering. Yeah.
so like imagine you say the capital of the state containing Dallas, right?
Mm-hmm.
Instead of is, um, you could say like, um, the capital of the state containing Dallas has a building that looks like fill in the blank or something like that. And then all of a sudden that feature now is needed in that sentence. Right. So you can
Hmm.
certainly do some fun things. In this article, I don't think they do that. But they keep the sentence fixed. Okay. But if I'm reading you right, I think that's like a fun experiment that you could do.
Yeah, I'm wondering if they have like, is there a good way? Do they go into how they like uh, uh, developed this attribution graph, i.e., like, could one, in theory, like reverse engineer such that I have a thing that I can stick on the end of my model that sort of shows me the attribution graph that they're sort of collecting here?
Oh yeah, absolutely. This, part of the goal of publishing is to make this technique accessible to anybody who wants to do the research. The
Mhm.
most expensive thing, though, is training that CLT. So if you can get their CLT for a particular given model, okay. So I think they have like an 18-layer mini LLM that they did a lot of their experiments on. So if they're willing to share that model and the CLT that they trained on that, then you could do whatever experiments you want, not just the ones that they did.
Interesting. Okay. And then yeah, so CLT is the thing that's sort of doing this monitoring. Do I have that
The
sort of
CLT is predicting the outputs of every MLP in a hopefully monosemantic way.
interesting? Okay.
Does the CLT include this local replacement part that's trained on specific queries?
The CLT is the local replacement model,
Ah,
basically,
okay, gotcha.
right? The
So,
columns of the encoder of the CLT are these circles in your replacement model. And those
okay,
circles are all connected with linear weights based on the residual stream and the attention patterns and whatnot. It's all linear connections. And so because it's all linear, you can very easily crunch the numbers and say, how much influence does the word Texas as an input have on anything up here? And you can
Ooh,
do the reverse. You can say, for the output token Austin, how much of that was influenced by anything in here? And you can also go in between. You can say from this circle to that circle, how much influence is there? And you
but
can
this
get a
is
number
different.
anywhere from 0 to 100%.
But this is one that has to be trained for each query, each type of query, each completion you
No,
want to
no,
do.
the CLT is not trained. It's only trained once.
Okay.
But when you do the input, they do calculate how far off was the CLT at each layer and each token position, and they introduce these diamond error terms to show how far it was off in its
Those are
predictions.
just constants then.
So those become constants once you've
for a given
calculated them.
query. Okay. Now I got it.
So in terms of like gradient descent training, you train the CLT once and then you are done. You can analyze this model on as many sentences as you want and you'll never run gradient descent again.
And the reconstruction error is quick to compute then.
Yes, very
Yeah,
quick to
got it.
compute.
Okay,
And
got
then
it.
the linear thing, they have a little bit here saying that like, here's how you can calculate it very quickly. It's the math, I didn't quite follow like 100%, but you can you can imagine that like it's not small, but if you had a linear system and let's say we had 40 million monosemantic features and there's 10 tokens, there's 400 million features in each layer, right?
Mhm.
So just use round numbers. If we were only 10 layers, so it's 4 billion, you know. So you have a linear system of 4 billion variables. It's
Mhm.
not nothing, but nevertheless, because it's linear, standard techniques can crunch through and find the weights. And so this is where they talk about you can see there's sort of a virtual set of weights between every pair of anything.
Yeah,
And you can calculate them relatively quickly and painlessly.
gotcha. Okay.
And so they're able to see how much does the word capital influence stuff that's happening up here, and how much does every single one of these things contribute to the ultimate next token prediction.
Yeah, I feel like being able to keep track of that, like if you deploy your model to prod and then you start collecting a bunch of data about like all these like related concepts that are popping up, I imagine that'd be super useful for like steering the model. That's where my head's
The
going.
thing that's less useful about it is we're going to read this article and they're going to say, here are these Texas features, here are these capital of a state features, here are these Austin features. They're all hand labeled.
Ooh.
So when you have 40 million monosemantic features times 36 layers, you have to hand label every single one of these, like whatever that number works out to be, 15 billion monosemantic features by looking at which sentences they fire on and analyzing what those sentences have in common or what the inputs are have in common or what the output logits have in common.
Well,
And
that's just an
so,
NLP problem, right? Basically, like
what's
if you
that?
that's basically like end of the day, that's just an NLP problem, right? Like if you collect enough data, you could big data your way through that, couldn't you? I feel like you could.
No. It's not. Yeah, you're right. It's not necessarily compute.
Like for this
Big O, it
experiment.
might be linear, but
Mhm.
it's still 12 billion things that need to be labeled, even if it's linear.
Fair point. Fair point.
Right? So it's 12 billion linear, and
I'll just
each
let
one might
Common
take
Code do it
you
for a month and we'll be
an
fine.
hour, let's just say. So
Yeah.
then if you have 12 billion things that take you each an hour, like, you know, let's go find a
Also,
grad student to go work on this.
Yeah,
this
exactly.
would this could also be useful much before, way before you label 12 billion pieces, right? Like if you labeled a few thousand, you would immediately have useful information.
Yeah,
Yeah,
what we'll
that's
see
fair
is
about
in a given sentence, right? There's only so many of these nodes that are really important. So it'll be down to dozens. Okay.
Hmm.
Most of the others are gonna get either super low weights, and so they're the white ones, and you don't even bother with them. And then there's going to be the trash can ones that don't lead to the prediction. So it'll come down dramatically. But I think Warren was asking about if you just wanted to do this on the fly as you get different inputs. There, the difficulty is if your intermediate nodes aren't labeled, you'll see a very nice tree, but you won't know what any of the branches in the tree correspond to.
Yeah,
So
interesting.
you can calculate this reduced tree very, very fast. You just won't know what it's a tree of.
Hmm.
We'll get to. I'll show you an actual graph, and then you'll see that like if these were unlabeled, it already it's not terrible, but it's not quite like snap your fingers, Bob's your uncle.
Right.
All right. So now what they're going to do next is they're going to say this graph is still a little bit complicated, and where you see these in the diagram, it's drawn as a box that looks like it's three-dimensional, right? It's got layers to it. That's where, for simplicity, not for accuracy. For simplicity, they combine monosemantic nodes into what they call a supernode. And so again, this is where I think earlier I was saying you might have a concept that represents things about San Francisco and the Golden Gate Bridge, but it seems to be kind of leaning towards architecture. And you might have a different one that's more about tourist attractions. And you might have another one about whatever, right? So they're not all the same thing, you know, um, but they're all what they have in common is Golden Gate Bridge-ish things. And so it's not accurate to just lump them together. But then, like I said, if you're down to dozens and you have 40 nodes, now this graph has what, 1, 2, 3, 4, 5, 6, 7, 8, 9? 9 is a lot easier to interpret than 40. Okay, that's the general gist. Okay, so in the article, they're going to show this type of graph with these rectangles, and generally speaking, almost everything is going to be multiple. It's going to be a supernode. So that actually represents 4 or 8 or 12 nodes that were similar enough that they manually combine them. Doesn't mean that their manual labeling is correct. Okay. But they show their work, so we can verify it. And did they show us one here? I thought. No, we'll get to it. We'll see what the actual graph looks like. So here there's a little bit about the math that they use in order to figure out these linear relationships and get the graph. Here we go. So this is what the graph really looks like. So you can see here there's like maybe 40, 50 nodes. And then they cluster. You can see 3 things together here, 2 things together here. That's what, about 6 things together there. And if they cluster them into these supernodes, then they can get the count down even further. Okay. So again, it is absolutely not true that these 3 things are redundant and identical. Nobody is saying that. They're just simply saying they're close enough that if we lump them, then we can hope to have some human interpretability. Right? What we're going to see is that for any given node or supernode, we have in the darker the orange what text they get activated on. And then up here is going to be what tokens what next tokens they promote. Okay. And then you can see up here, if we look at this graph, we'll see a section that shows which nodes fed into them. What are their inputs that cause them to actually have strong activations? Okay. So for example, here we see this dark green line, which is telling us that this supernode of these 2 features were very strongly promoted by this group of features here. Okay, so we have very high linear weights between this set of 3 and this set of 2. And so the idea is that if this set of 3 went away, if those features weren't present, then this feature might have actually not been present, might have had a very low value. And so this is now basically talking about, I may not be using this word strictly correctly, but a causal graph showing that non-zero values here cause non-zero values here, cause non-zero values here, which eventually caused a much larger logit for the next token to be the word Austin. Make sense? All right. So then they talk about they built a user interface, and here's the way that you can navigate this. I haven't completely looked at that, but so again, what we'll see is at least 3 kinds of features. Okay, input features, generally speaking, appear in the very early layers, first say 3 layers. and they fire when there's a particular word, as your actual input token. Okay. We're going to have intermediate features that are just concepts that are being stored, so to speak, in the intermediate representation, hidden representations, in the residual stream of various token positions. And then we have output features, which ultimately the other features are looking to promote. And these output features are the ones that are sort of shouting pick me as sort of what the next token should be. All right, so they mentioned we group things into supernodes for simplicity. And then in terms of the technique, I don't think it's as important here, but basically they're going to do they're going to do interventions. They're going to do experiments, causal experiments on the original LLM. And if you say, well, I saw a particular something in this monosemantic node of the CLT, okay, we know exactly what MLP that corresponds to. That's the whole reason why we built the CLT, was to be able to imitate the MLPs. And so therefore, if you know where it was in the CLT, we can go and we can modify the outputs of the MLP in a corresponding fashion to whatever that particular CLT was outputting. Okay, so there's a little bit of work you need to do to figure out exactly what did this node cause the decoder output to be. But you can do the math. You can say, a 0 here, the decoder looks like this. A 1 here, the decoder looks like that instead. Fine. Now that we know that, then we can add more of it, or we can subtract it from the outputs of the actual MLPs. So when we do these ablation studies, it'll be finding what the CLT outputs predict and then adding or subtracting values from the real MLPs, not from the CLT anymore, from the real LLM. And that's the thing, is that we know the token position and we know the layers where to actually make these changes. So here you can see, if I wanted to erase the influence of group, I could just take -1 times the output of group and inject it in the right place, and it's as if me zeroing it out. And one thing that might happen is this intermediate node, by the way, these are fictitious graphs. This intermediate node might then disappear when I disappear this. And this would be an experiment that kind of confirms the idea that group causes this say G concept to appear, because the absence of group causes say G to disappear. Again, if you say vision is due to my eyelashes and you cut the eyelashes and vision doesn't change, then you have a bad hypothesis. But if you say this one was caused by this one because I have a dark arrow there, then getting rid of this should in fact cause that to disappear. All right, there's a little bit more in here. It gets into some stuff that I didn't think was as important. And so I think I'm gonna stop here in terms of the technique, which sets us up in terms of time, fitting it into a session, and basically we are now perfectly set up for next week to say the On the Biology article does have a little section on the methodology, which we don't need to cover because we just covered it in detail. But for people who didn't read the companion article, it does a much shorter version summarizing it. And then it goes into interesting use cases where it says, here is a sentence, such as, fact, the capital of the state containing Dallas is. And then they're going to show you, here is a simplified graph with nice little rectangles so that you can see the patterns of influence of which things promote which things. And these intermediate things all ultimately end up significantly promoting a supernode that they call Say Austin, which are nodes that promote the logit for Austin. If you reasonably don't just trust everything that they're saying, we can click on And we can see the individual graph here, that's the 45 nodes or whatever, that are actually the exact equivalent. And we can see what they lump together as like these 12 Texas-related nodes. And we can look at them individually or whatever, and we can see what if I pick one, I think this one's already selected, that's why it's pink. You can see here a list of the nodes that most contributed to it. So these contributors have to be all down into the left of it. Okay. By the way, if you see down here the tokens, some of these token positions have so many nodes that they needed more left-right width. But all of these, regardless of whether in this 1, 2, 3, 4, or 5 column, they're all the same token position. They just needed more room to draw them all. Okay, so some places where there's not as much, they didn't really need as much room to draw them. Here you can see capital, they actually, again, took a little bit more room width-wise to draw them. And so next week we can go into if you take this and you analyze them and you manually annotate and say, these seem to have to do with the concept of a state in the United States. These seem to have to do with the city of Dallas. These seem to have to do with the state of Texas. These seem to have to do with the capital of a state, blah, 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 blah. Then you can simplify it into this diagram with supernodes. Then once we have a hypothesis that this is the computation graph, you can ask questions like, well, what happened if I what happens if I snipped out the influence of the word state? What if I replaced the influence of Texas with, and so then we will see ablations where they do exactly that, where they snip out different things, or they replace Texas with California, and all of a sudden the answer changes from Austin to Sacramento, even though we only in this tiny place change the vector values from the ones we see in sentences that have Texas in them to sentences that had California in them. That from pre-recorded our corpus, we got what these values are. And so we took those pre-recorded California-ish values and we just wrote them in a few selected places, maybe 4, maybe 8, maybe 12 places, whatever, you know. But relatively speaking, right, we're talking about a multi-layer LLM with, you know, millions of weights, right? So we wrote in relatively few places, and we got from Austin at whatever 92% to Sacramento at 97%, the next token prediction. So that kind of experiment for me is very strong evidence that their analysis and this particular computation graph, this tree, this circuit, is in fact relatively accurate to represent what really happened in the LLM. So they have a dozen different examples of different sentences with different kinds of patterns that they were able to find. And again, there's millions of sentences in their training corpus, and they published a dozen. I think there's still much that's unexplained. But what they did explain, they backed up very, very well with evidence that the computation is, in fact, the way they say it is. And so that's the tease for next week.